the lecture series on differential equations for undergraduate students. Today's topic is first order partial differential equations. In last lecture, we had learned about partial differential equations. There we had seen that partial differential equations do have solution in the form of arbitrary functions. We have seen in some of the first order partial differential equations that the form of f, that is the unknown function which is in the terms of arbitrary function, that could be decided using side conditions. In one example we had seen using initial condition we have done it. Then in some other examples we had seen as we are changing our differential equation, the argument of that function, arbitrary function, is changing, and we were pondering about or thinking about that can we find out a method which decides the argument of that function. Yeah, so today we are going to find out this method which we are calling method of characteristics. The characteristic is that unknown argument, that is in the arbitrary function, what is that argument. This method of characteristic actually says is that if I could change the differential equation in such a form that on a xt plane it is having one function or one curve on which it is ordinary differential equation. Let us see it one by one. We would try to see it with the help of our first example, that was first order wave equation, del u upon del t plus c times del u upon del x is equal to 0. We would like to know the unique solution. So, we could move to the initial value problem, that is we can define the initial condition as well, that at t is equal to 0 u x comma 0 is f x. Again here the form of f we have not taken known, we are just taking in general. Then what we try to do is we assume that this differential equation, the function is u x t, that is it is a surface on xt plane. We take a particular curve on that plane and try to see that with that curve this surface is changing to its curve, or that is a function. So, we just move in the xt plane, we take a curve and we assume that my function u x t is constant along that curve. So, in xt plane that curve we are denoting, or we are using the parametric equation of that curve. That means what we are saying is x is a function of r and t is a function of this. You do know that is this is called the parametrization of any equation of the function. So, let us take x is equal to x r and t as a t r, where r is the parameter of that curve. Then my u x t, that would be actually that u is a function of x and t, and x is a function of r and t is also a function of r. So, you can write like this one. What we are trying to do is we are trying to find it out along this curve, this function u x t becomes a constant. So, that we do say is that u x t, that is the surface, is same as that particular curve. Now, let us use the chain rule so that we can get the derivative of u in the terms of r. So, d by dr of u x t would be del u over del x times dx by dr and del u over del t times dt over dr. Now, compare it with this given equation, del u over del t plus c times del u over del x is equal to 0. Now, the coefficient of del u over del x, here is c and here it is dx by dr. So, I do get dx by dr is equal to c. Similarly, the coefficient of del u over del t here is constant, and here the coefficient of del u over del t is dt by dr. So, dt by dr would be 1, and d by dr of uxt is 0. So, we write it du by dr is equal to 0. Now, so what we have got? We have got actually that we are changing this partial differential, we are getting is a relationship between x and r, t and r, and u and r, that is with respect to that parameter we are getting all our first order ordinary differential equations. We do know how to solve them. So, let us try to see one by one. Let us first take dt by dr is equal to 1. What this implies? This says t is r. So, now our parameter we have fixed up as the second independent variable t. Now, dx by dr is equal to c. This says is that x should be cr plus x naught, that is a constant, and since r is t, the parameter is same as the second variable t. So, I would take it as ct plus x naught. This x naught, why I am taking this constant as x naught, because if we see x is equal to ct plus x naught in xt plane, then this is a line. So, this constant is nothing but the x intercept on the ct plane, on the xt plane, and the ordinary differential equation. Now, what we are remaining is with in the unknown function u, that is du over dr is equal to 0. What it says is that if I try to solve it, that u must be constant along this curve ct plus x naught. This is what we are getting is, that is when we are changing it to this one, we are getting this is constant along this curve x naught. So, now I will use the initial condition at t is equal to 0. At t is equal to 0, x would be x naught. Now, this x naught I would write from this equation as x minus ct. Then now I am using the initial condition for my partial differential equation, that says is u at x comma 0 is f x. Now, that means we are using t is equal to 0. At t is equal to 0, x is x naught, because we are now not working x and t are not separate, we are talking about that both x and t are along certain curve. So, we are talking about along this line. So, at t is equal to 0, my x is x naught. This is given as f of x, so it should be f of x naught. Now, x naught along this line is nothing but x minus ct. So, I would write it as f of x minus ct. Now, you do remember that is, this is how we have got that the unknown function, we have got the solution as f of x minus ct. The argument was x minus ct, and that f, the arbitrary function we have defined by the data, that is what is the initial condition f. So, now what we are talking about is, in this method we are saying is that our partial differential equation is, we are changing to an ordinary differential equation in such a manner that my unknown function u remains constant along that curve. That is, we try to find out a curve given this differential equation, we try to find out a curve such that my unknown function becomes a constant along that curve, and that curve is going to give me the argument of our function. So, in this particular equation, this which if you do remember, we have called it a first order wave equation, or it is transport equation. Let us see that is what it is actually doing. It is transporting the initial data f x along the x axis at a speed c, dx by dt, that is the speed of x with respect to the other variable t is c. Now, you see that is how it is coming up. If this is my x y plane, so we are getting is that from these points x naught we do have this characteristic, and so you again see it that from these points the data, this is the surface, you see, let us see how we are moving. You see, this is my characteristic line, x is equal to ct plus x naught, this is in xt plane. Now, as I move this line, So, this is what is actually the function u is this surface which is the function u. As I am moving from along this characteristic line in the on the x axis. So, from here to here this distance is x naught, that is why the intercept is x naught. So, now if I am moving towards this point, then my surface u, this is constant along this line. What we are getting is u would be at one particular point. If you see is this surface, this is a, just try to see it in the 3-dimensional one. So, what we are getting is that is my u variable, that is u dimension, we would be getting it here the constant along this whole line on this surface. So, what it is doing is it is transporting my initial data fx initial data along this x axis. So, we are getting is my surface is, you see that surface is changing. So, as we are changing from this point to this point, we are moving, we are just changing my moving my this line parallel to this one, then my surface is moving in this direction. Then when we are changing it one, the surface is moving in this direction. What we are getting is that is along this surface, this is changing, or this is the transporting my initial data on this surface. This is what we are meaning. So, this method is called the method of characteristic, and this line x is equal to Ct plus x naught, this is called the characteristic curve for this first order wave equation del u by del t plus c times del u by del x is equal to 0. Now, this initial value problem which we had started, that del u by del t plus c times del u over del x is equal to 0 in the whole region minus infinity, that is my x was on the whole real line, but t was positive only. T, as I said, is that x, y, z we are taking as the dimensional spaces, the coordinate Cartesian coordinates, and t as the time has to be positive. Then if I had used the initial condition at t is equal to 0, that time t is equal to 0, if it is fx, what we had seen in this one, that is if I could find out a characteristic curve in uxt space such that that curve has to be in the xt plane along which my surface uxt is constant, that is this fx remains constant at that for all x, then this is called this is having a unique solution, and it is called the Cauchy problem. Why this says is that along this characteristic curve, so let me call this characteristic curve, here it was coming as a line. So, in general let me just try to, because the whole idea of all these things is little bit above the level of here. So, I will try to explain the things with the help of examples only. So, let me just say as the general solution, that if along a curve gamma in xt plane, or that is in the plane of independent variables, if I could find out a curve along which the unknown function is constant with respect to all those independent points, then it guarantees that there would be, that initial value problem will have a unique solution. This is what is called the Cauchy problem. Now, let us see in the one example, that is how we are going to do. If you do remember, that is we have already done this one, we had find out that f of x minus, this is the characteristic, and from this characteristic we had find out that is x naught is x minus Ct, that is the argument, and with initial condition we could find out that particular function. So, now if f is continuously differentiable, that is the initial condition function f, this is continuously differentiable. What does it mean? It says is that its partial derivatives del u over del x and del u over del t, they are also continuous. Then we call it to be a classical solution, that is then uxt is equal to fx minus ct, that would be called a classical solution. Say for example, if you remember in the last lecture we had used one function as fx as e to the power minus x square. This is differentiable function, it is continuous, its derivatives will also remain continuous how many times we differentiate it. So, this is a classical solution. Moreover, if you do remember, we had used one more function f. So, let us say what we are saying is if f is only piecewise continuous, that is its partial derivatives may not be continuous. So, if you do remember, we have taken one example of this form, this function is continuous, piecewise continuous, differentiable, but its derivative, if you do remember, del u over del x as minus 2 times x minus ct in the region x minus ct whole square is lying between 0 and 1, or that is x minus ct is from minus 1 to plus 1, and if it is outside we are getting it that this is both of these derivatives, they are not continuous. Then we call this solution as a weak solution. Of course, it is satisfying the equation, but its derivatives are not continuous, then it is called the weak solution. Let us do one example. Solve the initial value problem 2 times du over dx plus du over dt is equal to 0 with x on the whole real line t positive, and initial condition at t is equal to 0 is given as ux comma 0 is 1 upon 1 plus x square. Now, we see this is again my first order wave equation. Let us just try to find out this one. The characteristic curve we are assuming in xt plane as xr and tr with the parametric forms. Then we would be having uxt as xr and tr. So, using the chain rule du over dr would be del u over del x into del dx by dr plus del u over del t plus dt by dr. Compare this with this given differential equation. Del u over del x I would get as, so let us try from here, dt over dr we are getting as 1, this says is t is equal to r. So, my parameterization r we are changing it to the second variable t, that is I can say is my function ux comma t can be given as ux a function of t and t in the single variable we are getting, and del u over del x is coefficient dx by dr is 2, which give me that x as 2r plus x naught or 2t plus x naught, because r is same as t from the first equation. Now, the ordinary differential equation which my partial differential equation has changed, that is change ordinary differential equation is du by dr is equal to 0. Its solution gives me that u is constant along my characteristic. What the characteristic we had find out? X is equal to 2t plus x naught. So, from here if I use the initial condition at t is equal to 0, x would be x naught. So, my characteristic x naught would be actually x minus 2t. So, what will be my solution? My solution would be ux naught at comma 0 should be f of x. F of x, if you do remember, we were having our initial condition as 1 upon 1 plus x square. So, at x is equal at t is equal to 0, x is x naught in along this curve. So, I have to replace it by x naught square, that says is this has to be replaced as 1 upon 1 plus x minus 2t square, because we want the general solution in the form of 2t. So, in the form of x and t. So, what we have got our general solution? We have got the general solution uxt as 1 upon 1 plus x minus 2t square. This is my unique solution in of the initial value problem. Since we can find out a curve along which the unknown function u is constant, that says is that unique solution does exist, and that solution we can find out in the form of its characteristic. The characteristic we are defining by this, because that constant value. So, we are using the initial condition at the characteristic level gives me the characteristic function or the characteristic of this one, and then again using it we get the functional form. So, we get the solution 1 upon 1 plus x minus 2 t square. Now, let us see what the graph of this function. So, if I use t different values for t at time t is equal to 0, it should be 1 upon 1 plus x square, this is the curve. At t is equal to 1, we are getting is the curve is this one. At t is equal to 2, this third curve, t is equal to t is equal to 1, t is equal to 0, t is equal to half, t is equal to 1, t is equal to 1.5 and t is equal to 2. These curves I have taken, that is at different t I have taken these curves. As it is a wave equation, this is the transporting equation. What it is doing is, so now you see is if I try to make a surface out of this, I would be getting this surface like this one, which is containing this kind of function. You can just imagine it in the 3-dimensional one, that is how this surface would be looking like. This is transporting this initial function towards its right, because my c was plus 2 over here. So, the speed at which it is transporting is along this x axis, that is it is at the speed of 2. So, we are getting it that this function we are transporting towards the right. Let us see one more example. Now, my differential equation is minus del u over del x plus del u over del t is equal to 0, and the initial condition is u x comma 0 is equal to 1 minus mod x for mod x lying is less than 1 and 0 for mod x greater than 1. You see here the again this is first order wave equation, c is here minus 1. Let us see what happens to this solution. Again we will go with this method of characteristic. So, we will assume the characteristic curve to be of the form xr tr, and then we get this first order equation, ordinary differential equation du over dr is equal to del u over del x times dx over dr plus del u over del t times dt over dr. Now, compare this ordinary differential equation with the given partial differential equation, we get the characteristic. What it gives? Dt over dr as 1, which says t is equal to r. So, the parameter we are fixing at the second variable t. Derivative of the coefficient of del u over del x dx by dr is minus 1, gives x as minus r plus x naught, r minus t plus x naught. So, this is my characteristic curve. Now, the comparison of du over dr is equal to 0, that says as my partial differential equation has been changed to the ordinary differential equation, du over dr is equal to 0, r has to be t. So, we get that u should be constant along this characteristic curve, x is equal to minus t plus x naught. That says is x naught must be equal to x plus t. What we are getting at t is equal to 0, x is equal to x naught, and the characteristic we would define as x naught is equal to x plus t, or this is x plus t is our characteristic. So, what will be our solution? So, at t is equal to 0, x is x naught. So, u x naught t would be 1 minus x naught for x naught less than 1 and for 0 for x naught greater than 1. Now, that says is now change this to the characteristic x naught to x plus t, we would get the solution as u x t as 1 minus absolute value of x plus t for x plus t lying between minus 1 to plus 1 and 0 for x plus t lying between outside the region minus 1 to plus 1, or you could say is that is here is that x is lying between t minus 1 to t plus 1 and x is lying outside t minus 1 to t plus 1. Let us see that is how this function is looking like. We are having this is at t is equal to 0, that is initially function is minus 1 to plus 1, because t is equal to 0, what we would be having is that is function would be 1 minus absolute value of x for minus 1 to plus 1. When t is equal to 1, we would have that the function would be 1 minus x plus 1, absolute value of x plus 1 in the region x plus 1 is lying between 0 and 1 or x is lying from minus 2 to 0. So, what we are having is at t is equal to 0, it is this one, at t is equal to 1 the function has shifted towards the left, at t is equal to 2 the function has shifted again more left to this one. Now, we have seen the first order wave equation in which we have seen that C to be positive when I have taken C as 2. Whatever be the initial condition is just giving me the wave shape of this wave, that is all, and it is wave is shifting, that is what you are saying is that is if the wave is like this one then it is going out, if it is triangular one it is just going like this one. So, what we have got when C was positive, in all our examples where I have not given any particular value of C, all the places I have taken C to be positive, or more explicitly I have taken in all the examples in the last lecture also as C as 1. We had got all the time that from t is equal to 0 as we are moving towards the positive values of t, I am getting that my equation was, my wave was moving towards the right. Here I have taken the first example where my C is negative, and what we are finding out that it is shifting towards the left. So, let us summarize from these examples what we have got, that in the first order wave equation for C to be positive wave moves to the right, and for C negative wave moves to the left. So, the sign of C defines the movement of wave. So, that is why this first order wave condition wave equation is actually called as, that is transport equation, whether it is transporting towards the right or transporting towards the left. Now, let us come to another problem where this it is not only initial value, but we are having is initial and boundary value problem. What the difference? In the first kind of equations what we have seen, that is again I would be going with this this first order wave equation, we had that my x was on the whole real line. Now, suppose I do come to the semi finite plane, that is let us say that is semi finite plane, let us say that is positive plane. So, again I am using this my first order wave equation, but now my x is also positive and t is positive, then I would put one boundary condition on x also. So, what will be the initial condition is this boundary condition would be that u at x is equal to 0, t is a function g t, and initial condition is that u x comma 0 is f x. Let us see that what the solution would be. Does this data give me a solution? First I will consider the case when C is positive. We have seen in the last example that C positive and negative was giving me the wave is moving towards right or left, that was in the initial value problem. There I was not having this condition of this boundary condition. Moreover, the x was on the complete plane, that is from minus infinity to plus infinity. Again I will go to this method of characteristic. So, we will use the characteristic curve as the parametric form, x is x r and t is t r. So, u x t would be u x r t r. Using the chain rule, again we would get d over d r of u x t is del u over del x d x by d r, del u over del t d t by d r, which will give me, now compare it, d t by d r as 1 and d x by d r as c. So, both these equations would give this, give t is equal to r, and from here we would get x is equal to c r plus x naught, or r is same as t. So, this would give me x as c t plus x naught, again this x naught is the x intercept. So, the characteristic I am getting is x naught as x minus c t. You see, that is when we are changing, since my equation was not changing, whatever be the other conditions, my characteristic will always be same. So, the characteristic is actually because of the equation. The ordinary differential equation would be du by dr is equal to 0. That says is u should be constant along this characteristic line or this characteristic curve. So, at using this initial condition and now I do not have only the initial condition, I do have this boundary condition as well. What it is actually doing is, let us just try to see this characteristic equation. This is a line. Now my plane is only the positive side of x and positive side of t. Let us see this characteristic, that is x naught, this is a constant x minus c t, it is actually dividing my entire x t plane into. So, this characteristic is actually dividing my whole x t plane. You see, we do have this line x is equal to c t, that is when the constant x naught is 0. This is dividing the whole plane into two parts, one is region R 1, another I am calling the region R 2. In this region R 1, x is greater than c t, or you could say is that my x minus c t would be positive. What it says, this characteristic line over here, this would be originating from the x axis, and in this region R 2, x minus c t would be negative, or the characteristic line in this is originating from the t axis. That means, in the region R 1, this characteristic line, because we if you do remember, for initial value problem we had used that the characteristic that from the initial condition. Now, initial condition where we have to take, in the region R 1 it is originating from x axis, that is I could take x is equal to 0, that means I have to use in the region R 1 the boundary condition, and here it is originating from the t axis. So, that says is t is equal to 0, this would decide from where my characteristic is originating or what should be my x naught. So, I would get here this line would be deciding with using my initial condition. So, thus what we are getting is that my solution would be decided by both boundary condition as well as by the initial condition. Boundary condition we would be using in the region where of R 1, that is when x minus c t is positive, and we are using the initial condition in the region where x minus c t is negative. So, what we are getting is in the region R 1 x is greater than c t and my characteristic was originating from the x axis. So, we do use t is equal to 0 we get, and in R 2 this x is less than c t and we would be going to use this boundary condition. So, the solution would be now u x t as f of x minus c t, that was my. Now, you see you will find out that is how I had find out this x minus c t. As I said is in the region R 1, that is when x is greater than c t, I have to use initial condition. Initial condition at says is that at t is equal to 0, if I see my characteristic x is equal to x plus x naught plus c t, x would be x naught and that x naught we would be saying is x minus c t. So, this is actually we had already done in our initial value problem. So, my solution would be f of x minus c t. Now, let us come to this region R 2, x is less than c t, this is what we are writing here. I have to use the boundary condition because the characteristic is originating from the t axis. So, I have to take x is equal to 0. At x is equal to 0, what is the value of t? So, value of t, how do we find it out? At x is equal to 0, let us say value of t is t naught. How do that find out this t naught? So, let us see, at x is equal to c t plus x naught. So, at t is equal to 0, x naught is x minus c t, and at x is equal to 0, what I would get? X is equal to 0, I would get c t plus x naught is equal to 0, that is t is equal to minus x naught by c. So, t naught would be actually, now x naught what we are getting is x naught, if I am going to use, because this is has to be the same characteristic. So, x naught has to be decided by this, x naught is nothing but x minus c t. So, whatever be this x and t, that x minus c t has to be same. So, x naught I am using x minus c t. So, if I am using x minus c t, that gives, that is my t naught would be t minus x by c. So, we are getting is that at x is equal to 0, t has to be t naught. So, u 0 t is g t. So, at t naught it should be g of t naught, and t naught is nothing but t minus x upon c. So, what we have got the solution? We have got the solution u x t would be f of x minus c t when x is greater than c t, and it would be g of t minus x by c when x is less than c t. Let us see, is this actually the solution of our differential equation, and is it satisfying both the boundary conditions, that is it really the solution of our initial boundary value problem? Let us try to see. This is what we have got, my u. So, here f and g are general. What would be del u over del x? F dash means derivative with respect to x minus c t. Del u over del x means derivative of f with x minus, with respect to x minus c t, and derivative of x minus c t with respect to x, that is 1. This is in the region x is greater than c t. In the region x is less than c t, I will differentiate g. So, I am using both the places this dash for the derivative, but you have to get the reference, that is the derivative has to be with respect to that argument. So, here this derivative with respect to t minus x by c, and the derivative of t minus x by c with respect to x, that would be minus x by minus 1 by c, since t is constant over here. So, it is minus 1 by c g dash t minus x by c. Whenever I am using this f dash as g dash with different arguments, that it says is the derivative with respect to that argument. Now, get del u over del t in the similar manner, the derivative with respect to x minus c t, and the derivative of x minus c t with respect to t would be minus c, and the derivative of this with respect to t minus x by c is g dash t minus x by c, and derivative of t minus x by c with respect to t would be 1. So, this is this one. Now, you see, if I take c times del u over del x, I would get it c times f dash x minus c t, and here it is in the region x is greater than c t, and the same reason del u over del t is minus c times f dash x minus c t, that says is they are this plus this would be 0, that is c times del u over del x plus del u over del t would be 0 in the region x greater than c t. Similarly, in the region x less than c t, it would be minus g dash t times x minus c, and this would be plus g dash t minus x by c, that says is again the sum of these two would be 0. Hence, what we are getting is that this solution is satisfying my differential given partial differential equation. Moreover, when I take t is equal to 0, t is equal to 0 means x is greater than 0, and here this region will transfer to x is less than 0. Now, if you do remember, our differential equation was for the region x greater than 0, that is when t is equal to 0, this portion is not there, or this is not the region in which we are interested. So, at t is equal to 0, u x would be f of x. This is what is my initial condition. Then at x is equal to 0, x is equal to 0 says is c t should be less than 0, whatever be this c, whether positive or negative, t less than, if c is positive, we have started with the c as positive. So, c is positive, so it says is that c t is less than 0, that says t is less than 0. So, this is redundant reason because we are taking is t to be positive. Then when 0, this is the only reason which would be of interest for us, that is t is positive. Here when x is equal to 0, I would get only g t. So, u 0 t is g t, that is the boundary condition we are satisfying. So, this is satisfying my boundary conditions, initial condition and the differential equation. So, this is the solution of this initial boundary value problem. What we have got is, if we do have initial boundary value problem for the first order wave equation, the method of characteristic set, that is we could find out a characteristic for C positive which satisfies both the conditions, initial condition and the boundary condition, and we have got the solution. So, this is solution for this one. Now, let us do one example. Solve this partial differential equation 2 times del u over del x plus del u over del t is equal to 0 for x positive and t positive with boundary condition u 0 to t as e to the power minus t and initial condition u x comma 0 as 1 minus x in the region 0 to 1 and 0 for x greater than 1. We will go with the solution. As usual, we will first find out the characteristics of this equation, so that we could find out. So, for characteristic curve again we would use as x r and t r. So, we will change del u over d over dr as del u over del x times dx over dr plus del u over del t times dt over dr. Compare this with given equation, I would get dt by dr is equal to 1, implying t is equal to r. Dx by dr is 2, gets x is equal to 2 r plus x naught, r 2 t plus x naught, this is the constant x naught. So, the characteristic curve we have got x is equal to 2 t plus x naught, that is again you see is that this characteristic curve for this equation we had already found out in one example. Now, given partial differential equation is changing to the ordinary differential equation du over dr is equal to 0, which gives that u would be constant along the characteristic, x is equal to 2 t plus x naught. Now, to find out this characteristic we would use, that is, now rather than again going with the solution, that is x is equal to x minus 2 t is dividing my entire plane into 2 regions. In one region the characteristic would be originating from the x axis, that is I would use t is equal to 0. In another region the characteristic would be crossing from the originating from the t axis, that is I have to use this x is equal to 0 condition to determine that particular characteristic. So, we do know that is how to do it. So, we are getting as x minus 2 t. So, the solution, if you do remember, we in the last slides we had find out that is f of x minus c t for x greater than c t. So, the c would change here to 2, c is 2 actually, and g of t x minus c for x less than c t, and again c is changing to 2. So, let us put up in our one, what is my f? Our solution would be our u x 0 was 1 minus x in the region 0 to 1 and 0 elsewhere. So, we have got it when x is greater than 2 t, that is it is 1 minus x minus 2 t, and the boundary condition was u 0 t was e to the power minus t. So, we would be getting e to the power minus t minus x by 2, this x by c. So, x by 2 for t greater than x by 2, or that is x is less than 2 t. So, I am writing it as t is greater than x by 2. So, let us see that is what is this function is actually. X minus 2 t is lying between 0 and 1, that says is 2 t is less than x is less than 1 plus 2 t, and it says is x is less than 2 t. There is some region is still left. So, what we have been left for the region x greater than 2 t plus 1, it would be 0. For the region x lying between 2 t to 1 plus 2 t, the solution would be 1 minus x minus 2 t, and for the region x is less than 2 t, this is not t, this is x, x is less than 2 t, it should be e to the power minus t minus x by 2. We can check that this also satisfies our partial differential equation, and moreover it is also satisfying both the initial condition and the boundary condition. Now, let us take the case of this initial boundary value problem when c is less than 0. The characteristic would be the same, x is equal to c t plus x naught. Now, c is negative, so I have taken is minus c, so that we can make it more visible. So, when c is negative I am taking it minus c, so c is positive and it is minus c. what will be my characteristic? My characteristic would be x plus c t. Let us see this characteristic, what it is doing in our x t plane. In my x t plane, this is the characteristic x plus c t for some constant x naught. So, you see is that is here this, if I take t is equal to 0, this is 4, and at so we are getting is that is this is one characteristic, this is another characteristic. Now, my characteristic is moving in this manner along the x axis, they are moving in this manner, parallel lines. What they are doing is, this characteristic is also crossing the t axis, characteristic is also crossing the t axis, that is the same characteristic is at the x axis, at the t axis. Now, in the when c was positive, we have got that clearly, it was divided like this one. So, we were having is that the characteristic is either crossing the x axis or crossing the t axis, and that says is I can use either initial condition, initial condition or the boundary condition. Here what I want along this one, I want x naught and t naught such that both the initial condition and boundary condition is satisfied. What it says is, if I take t is equal to 0, then my x should be x naught, and if x is equal to 0, then my t should be t naught, but we could not find out any of these things, that is any line which is satisfying what t is equal to t naught. What we would be getting is that is my function should be f x at this point and g t at this point, which is not possible, that the same one, because when we are saying is it is a constant, the same constant could be what the value of the two function at two different points. So, thus for c negative, there is no solution for initial boundary value problem, where the partial differential equation is the first order wave equation, and we are using both the initial condition and the boundary condition at x is equal to 0. Let us see the method of characteristic in semi-linear equation. Again we will explain with the help of an example. So, this is a semi-linear equation, that means the equation whose coefficients are involving only x and t. So, 2 x t del u over del x plus del u over del t is equal to u. Reason is this one, with u x 0 is x. Now, so again try to find out the characteristic. So, using the same method, that is characteristic curve on the x t plane with x r and t r, using the chain rule, du over dr will be del u x del u over del x dx by dr, del u over del t dt by dr. If I compare with this one, what I would get it as from here, that dx by dr is 2 x t, dt by dr is 1, and du by dr is u. So, what we are getting from here, that dx by dr is 2 x t, dx by dt is 2 x. So, t is equal to r, that is dt by dr is equal to 1 is giving. So, we would get it dx by dt is equal to 2 x t. Try to find out the solution of this, we would get dx by x is equal to 2 t dt, that says is differentiating on both the sides, log x would be integrating on both the sides, log x would be t square plus c. This says is x is equal to x naught times e to the power t square. Again I have taken it x naught just to keep the similar manner as we are using in the line equation. Of course, this is some constant which is e to the power c. So, x naught we have taken because we want the curve in x and t. So, we are taking it as an x naught. Now, if I use the initial condition at t is equal to 0, I would get that x is equal to x naught, because t is equal to 0, e to the power t square would be 1. So, x would be x naught, that says I want x naught. So, x naught I would get from this equation itself, x naught would be x times e to the power minus t square. So, this is what is my characteristic. Now, so you are getting is that is when we are change this equation, I have got the characteristic as x times e to the power minus t square. Now, given partial differential equation was changed into the ordinary differential equation, that is du by dr is equal to u. Now, r is same as t. So, I would be writing it as du by dt is equal to u. Again this is first order ordinary differential equation. We can find it out using the variable separable method, and we can just integrate on both the sides. So, that says is du over u is dt, integrating on both the sides, log u is t plus d some constant, that says e is equal to 8 times e to the power t, where a is some constant. How to determine this constant? For this again we have to use the initial condition. Initial condition says at t is equal to 0, u would be a. At initial condition t is equal to 0, u x comma 0 was x, that was the our initial condition was given to us for this one. So, at t is equal to 0, x is x naught and u x 0 is given as x. So, use it, a would be u at x naught comma 0, x naught is nothing but x times e to the power minus t square. So, it would be u of x e to the power minus t square 0, which is given as x. So, it should be x times e to the power minus t square. So, this is what we have got, the constant a we could determine. Hence, finally, what would be our solution? Our solution would be u is equal to x times e to the power minus t square into e to the power t. So, we would get u x t as x times e to the power minus t square e t, or x, rewrite it as x times e to the power minus t square plus t. So, this is the solution of our given semi-linear partial differential equation with initial condition. So, this initial value problem does has this unique solution. We can check that this is actually the solution of our given equation. So, what we have been given? We are getting the equation is 2 x t del u over del x plus del u over del t is equal to u. We have got the solution as x times e to the power minus t square plus t. This function is, we do know, is continuous differentiable, and actually it is continuously differentiable, that is it is derivatives are also continuous. So, this would be actually a classical solution. So, let us see find out del u over del x. So, that is derivative with respect to x of this function. So, treating t as a constant. So, here is only x. So, it would be 1. So, it is e to the power minus t square plus t. Then the derivative of this u x t with respect to t. So, x is constant, that is as such, e to the power minus t square plus t, its derivative is with respect to t square minus t square plus t would be e to the power minus t square plus t. The derivative of t minus t square would be 1 minus 2 t. So, we are getting is x times 1 minus 2 t e to the power minus t square plus t. Let us substitute these derivatives in our given equation. 2 x t times del u over del x, that is e to the power minus t square plus t, plus del u over del t, that is x times e to the power minus t square plus t minus 2 x t times e to the power minus t square plus t. This and this term gets cancelled. What is being left is x times e to the power minus t square plus t, that is nothing but my u. So, it is satisfying our equation. Moreover, it is satisfying our boundary conditions as well. So, today we have learned solving the method of first order partial differential equation. We had learned that is in the linear first order partial differential equations, we can find out the characteristic by taking that characteristic means is that is there is a curve in x t plane or in the plane of independent variables, along which we take that the function has to be constant. So, we are changed our equation to ordinary differential equation, and from there we tried to find it out the characteristic, and that characteristic we had find it out using the either initial condition or both initial and boundary value conditions. We have learned the method for the linear differential equations, linear partial differential equations, semi-linear partial differential equations. Then one method is being left is in the quasi-linear partial differential equation. The next lecture will consider this one, and then we will move to the second order partial differential equations. So, that is all for this lecture. Thank you.